Okay, welcome to our lecture, fact, and today's lecture number 15. In the previous lecture, it was discussed uh, that Thyristor control reactor and Thyristor control Thyristor switch reactor. Now, uh, for today topic is Thyristor switch capacitor. Thyristor switch capacitor, that is TSC, Thyristor switch capacitor. So in the Thyristor switch capacitor, a single phase Thyristor switch capacitor can be drawn for our simplicity. Say this is the line, because it is a shunt compensation. We are discussing the shunt compensation. The capacitor to be switched, and it is connected with the Thyristor valves. No doubt, the Thyristor valves, it is already discussed. One Thyristor can handle 4 kV to 9 kV voltage and current from 3 kA kiloampere to 6 kiloampere. So as per the requirement of requirement, or say the voltage rating of the line, it may be connected in series. Number of thyristors are connected in series to obtain the required voltage, and then it is called as a thyristor valve. But the condition is that the gate pulse or switching on should be done simultaneously, otherwise the capacitor, the thyristor may fail. So this is very important. This is the capacitor. This is thyristor switch we are considering, or the voltage across thyristor switch. And this is the reactor. The reactor is connected to limit the current, and it also avoid the resonance in the system. There may be some resonance because of the capacitor is going to connect. So it is necessary to connect a small value of inductor in series with the capacitor. Now here bidirectional valves are there, and the limiting one surge resistor reactor is connected. Now, what is the wrong condition for the switching of the capacitor? Because we want transient free switching of the capacitor is very important. Now, say for example, the voltage across capacitor V is equal to V maximum, or that is the voltage V into sine omega t. This is the voltage across the capacitor, and the current I omega t is equal to V sine omega t divided by reactance of inductor plus capacitive reactance. Okay, and it is equal to V sine omega t divided by j omega L, inductance. L is the inductance, and 1 upon j omega c. And finally, we can write the equation of current I omega t, which is equal to, say, it is 1 upon omega square LC into 1 upon omega square LC minus 1 into V omega C cos of omega t. Okay. Now, it can be written as I omega t is equal to V, this is V, into n square upon n square minus 1 into omega c cos of omega t, and where n is equal to 1 upon under root omega square LC, or it may be the under root xc upon xi. This is one. So if n is large, we can say that the voltage across switched off capacitor is the nearly equal to the rated voltage. This is the meaning. Now, how it can be understood? Say, for example, the capacitor is switched on. Say, this is the voltage, the system voltage. This is the system voltage. And now, this is the current, capacitor current. This is the capacitor current I, and this is voltage V. And the voltage, when the capacitor is conducting, means the switch is closed, the current in the capacitor is I. Definitely some voltage is going to drop across this limiting reactor, and this limiting reactor voltage drop is very small, and it can be represented here. Is the voltage across this one is very small, so this is voltage across inductor. Okay, so now when the current becomes 0, the voltage across capacitor is equal to system voltage, and this is called as a charge voltage across the capacitor, or the capacitor is charged even if the supply is disconnected. Now this voltage VC play a very important role in switching on the capacitor and switching off the capacitor. How it is? Because if we are switching the capacitor during this time, the current become the transient current, or the transient will be 0, and we can say that the switching of capacitor is transient free. Otherwise, it will increase the transient in the condition. Now, this is some things which is related to the capacitor switching and capacitor switching on. Now, here it is quite clear that as this is connected with the shunt, with the transmission line, so the capacitor is get connected, which will supply the reactive power, or we can say that it is generating the reactive power and delivering to the transmission line. So in this way, there is a shunt compensation can be provided. Only the difference is that as compared to the Thyristor controlled reactor, it is a control is in a smooth manner, whereas in the capacitor, either we can connect the number of capacitor in some sequence of switching. So, but the switching of the capacitors are step, and it is quite difficult, or say there is some different arrangement is needed to obtain the smooth control over the capacitors or over the capacitive reactive power to be injected in the transmission line. So when there is a inductor, it is going to absorb the reactive power, and when there is a capacitor, it is going to generate the reactive power, or it is going to supply the reactive power to the transmission line. Now, the voltage across capacitor also play, say for example, if you take the some more waveform to understand the capacitor switching. This is, say, this is the system voltage. This is the system voltage. Initially, the capacitor is charged, and initially the capacitor is charged equal to the system voltage VC, whereas this is the system voltage V, and say it is equal to the rated one, it is 0.0, it is 0.5 pu, and this is 0. Now it is minus sign, it is 0.5 and 1 pu. Okay, this is the 1 pu. This is peak to peak value is there. So this is minus sign. Okay. Now, when the capacitor is fully charged, means it is not discharged, and during that time, the current in the capacitor is, you can represent as, during this one, the capacitor is current is off. Here the capacitor is connected. Now it will give the current. The magnitude of current is depend upon the size of capacitor. Okay, so this is the cap current in the capacitor, or the current is going to flow from this our circuit. This is I. It is a shunt connected capacitor over this one. So this is the capacitor is charged in the positive direction, and similarly, if the capacitor is discharged, a capacitor is charged in the negative half cycle, the same waveform can be obtained, and it is says that, say, now it is better to draw one more waveform to understand very well, because we can draw some conclusion from this one. Say again, I will just draw the same voltage. This is the system voltage, and it is 1 pu. This is minus 1 pu. Okay. Now the capacitor voltage is charged previous, because of the previous value. This is the capacitor voltage VC, and when we switch on the capacitor triggered, during this time the current is 0, and now the current get started in this way. So see, this is the switching on for the positive half cycle. In the positive half cycle, this is switching on during the negative half cycle. So it is found that the current is transient free. So for the transient free condition, if we want the transient free switching of the capacitor, we can understand with the help of this diagram. Say this is the system voltage. This is the system voltage, and similar to this one, and this is the capacitor voltage VC. This is V and this is VC. This is the charge condition before switching on the capacitor. So when VC voltage across capacitor or charge voltage is less than system voltage, so if you start if you switch on the capacitor during this intersection of VC and V, it will give the say transient free switching of the capacitor. So this is one condition. This is condition number 1. Second condition, Say this is the system voltage waveform. Yeah, this is the system voltage waveform is there. This is the maximum value. It is equal to 1 pu, and this is the voltage of the. Now, this is the charged capacitor voltage VC. So when it is crossing to the maximum value of the voltage, that is this point, if you are going to switch on the capacitor by triggering the pulse, by providing the trigger pulse to the SCR or walls are there, then again it will give the transient free switchings. So these are the condition to obtain the transient free switching of the capacitor. Now, it is what we will do, we will take some other example when the capacitor is fully discharged. The meaning is that whenever we handling any type of capacitors in the power system, or it may be somewhere where the capacitors are connected in the machines and say somewhere in the circuit, it is advised that the capacitor should be discharged before handling it. Say for example, someone is disconnecting our single phase capacitor start motor, so it is better to discharge the capacitor. Similarly, someone is doing maintenance work over the power factor controller devices, especially that is called as the APFC, automatic power factor controller. As soon as the capacitor is disconnected, it is better to discharge either by some transistor or some by some resistors to be connected across the terminal of the capacitors, or by any arrangement for the safety point of view. Now, let we consider the condition of the capacitor is fully discharged and partial discharge. Two conditions we will consider. First is the fully discharged. So our basic voltage equation, basic voltage waveform for the system voltage. Say this is the system voltage V. This system voltage is V. It is 1 pu. This is 0.5 pu minus 0.5 pu. This is voltage V 0, and this is the minus 1.0, or this is 1 pu is there. Okay. Initially, the capacitor voltage is 0. The capacitor voltage is 0. So we can consider here the capacitor voltage is 0. VC is equal to 0. Now, when we switch on the capacitor, during this condition, it will take a transient. It will produce the transient current, and this transient current will take more oscillations in the positive half cycle as well as negative half cycle, and somewhere it is going to settle, or it will give the system like that. So this is the current which is going to flow into the circuit. What is our circuit? Circuit comprises of capacitor, that is a static capacitor which is connected in shunt. So it is a shunt compensation in the system. Bidirectional valves are there, and with the help of bidirectional valve, we have connected one inductor to limit the current or to avoid the resonance. See, this is the current which is going to flow over this one. This is Thyristor switch. Okay, and this is the inductor, and system voltage is V. This is the voltage V. So it is means that when the capacitor voltage is 0, when the capacitor voltage is 0, charge capacitor voltage is 0, it will produce the large transient in the system. Whereas if the same voltage level, means the same system voltage, the previous voltage across the capacitor is 0.5 pu, the voltage of the capacitor VC is equal to 0.5 pu, say somewhere here. Under such condition, the current in the system is smaller. So the current in the system is, the transients are smaller as compared to the previous case, and it will settle very quickly to the smooth manner. So we can say that the capacitor voltage, if the capacitor voltage is equal to the system voltage, there is a transient free. If the capacitor voltage is greater than the system voltage, the right position to switch on the capacitor at the maximum crossing, where dV upon dt means rate of change of voltage is smaller, and it will give the transient free this one transient free switching of the capacitor. The next point, which is very important in the above discussion, is that, say, in this case, the condition for the transient free switching of the capacitor is, which we can summarize, is that VC should be equal to the system voltage. VC should be greater. When the VC is greater than the system voltage, the right position is maximum value of the voltage. And the maximum possible delay in the switching is the capacitor is 1 full cycle. It is clear from this diagram. Either for the transient free switching, either we have to start the capacitor at the maximum point, x the maximum value of voltage. This is the maximum value of voltage. Or at the negative, it will be a negative maximum voltage. Or you can start from the next maximum value. Means you can start from here, number 0.1. Second, either it may be the negative side, either it may be the next positive maximum value. So in this case, there is no in between switching of the capacitor from, say, this value to this value and so on. Therefore, we can say that the delay in angle, that is called as a firing angle. We cannot delay the firing angle by any value. Therefore, it is not possible to obtain the smooth control over the capacitor, isn't it? Why we are using the thyristor switch react capacitor? The reason is that the switching of capacitor, either the maximum peak value of the voltage in the positive cycle, peak value of voltage in the negative cycle, or from, it may be started from the next peak of the voltage waveform, isn't it? So, and hence there is a no delay angle is provided in the gate pulse, and therefore the thyristor switch capacitor is possible. Thyristor control capacitor is not possible. This is the very important point. Now we will look at to the its voltage and current area. Say similar to the this one, it is the current. Okay, this is the current, and this is voltage. So it is V is the voltage, and this is current. It is opposite to the inductor, and this is the characteristic. Sorry, this is the straight line. This is V maximum. This is I maximum. And VC maximum, this is VC maximum, and this is IC maximum, where VC maximum is the voltage limit and IC maximum is the current limit of the capacitor, and here it is the BC. So BC is the admittance of capacitor. Okay, BC is the admittance of capacitor. So this is the VI characteristic of thyristor switch capacitor. It is opposite to the thyristor switch reactor. So there is no area is going to define for the smooth control. As there is no smooth control over the capacitor, it is just a straight line. Now this is I just show with the help of some PPTs. So here thyristor switch capacitor is there, where the current is equal to V upon V n square minus 1 upon into omega c cos of omega t, and this is it is going to define the voltage across the capacitor. So see, this is our system, and it is going to handle the current I. This is the current. Voltage across capacitor is Vc. If it is charged because of the earlier energization, and this is the two walls are connected in the bidirectional, and this is the limiting reactor. Now this is the condition, this is the transient free condition. Transient free conditions. The condition is that if the capacitor voltage, that is a charge capacitor voltage, is equal to the system voltage, or it may be less than some system voltage. This is our system voltage, and the right position to switch on the capacitor is the intersection. It is the intersection, and it will give the transient free switching. Second condition is that the charge voltage is greater than the system voltage, and during this one, this is the system capacitor voltage, this is the system voltage, and the right position is that when the voltage passes to its maximum value and firing angle, delay in angle is equal to 0. So anywhere the delay in angle is equal to 0. And this is the VI characteristic or VI area operation for the thyristor switched capacitor. So there is no area is defined. Otherwise, if it is defined, it means that this is the controllable area. Now here, there is no control over the capacitor value. Either you can operate in the full conduction, or it going to switch off condition. This is why the area is not defined. But if we are using number of capacitors, say for example, the circuit is like that. This is the capacitors, number 1. This is, it is going to handle with the help of thyristor wall, bidirectional thyristor walls. This is 1. Similarly, the second capacitor is there, and this is C1, this is C2, and again there is a thyristor walls. Some limiting, either the individual limiting reactors are there. Okay, so by using the different combination, no doubt we can use different value of capacitor, and somewhat we can go in step to control the VAR generation in the transmission line. So this is the in the next time we will see some fixed capacitor and thyristor control reactor. It means that one fixed capacitor is there, and we are controlling the effective value of compensation, effective value of VAR generation by controlling the reactor value.